Okay, so in 2 seconds, I thought you might have a reasonable thought. If A is n by, oops, we were doing m by n, right? Alphabetical order is the thing. Where does this map? Right, if I think about this matrix as a function, what's the domain here?
It maps n to m.
Maps n to m. Yes? Okay. Oh, but we just learned about transposes, right? So A transpose as a matrix is how big?
N by m.
N by m, which means that it maps R m to R n? That's kind of weird. A goes this way? A transpose goes that way?
They're not necessarily inverses, are they?
Good question.
Yeah, I'm trying to think of it in terms of like algebra 2.
Yeah, so the like algebra picture, right, would be that, well, obviously these are inverses of one another.
Yeah.
Why would I think that these are not inverses of one another?
Because then you have something for inverse.
Yeah, I already have a symbol for inverses, so why would I have this new symbol? Also, these matrices aren't necessarily square. And inverses are only defined for square matrices. If they were square, I might have a case for this. That's still not true. They're not generally inverses of one another. But this is a useful behavior. So knowing that A maps that way and A transpose maps this way is sometimes useful for us, because we can do things like make a square matrix by multiplying A by A transpose or A transpose by A. You guys see that? Like if I do A, I get over there, and then if I do A transpose to it, I get back. So there's this funny property that like I can make a function here that's A transpose done to the result of A. Right? A brings me over there, A transpose brings me back. I can make a similar circle on this side. The circle on this side is going to be AAT. Because I do A transpose to take me over there, A to take me back. Those are going to have some interesting properties. We're going to talk about these matrices a bunch, but don't get attached to the idea that they're inverses. That is so special a case that we give it a special name later. It's good for this? Okay.